Have you ever wondered how your favorite e-commerce site or search engine handles search? How it instantly returns results as you type into the search bar? In this series, I'll break it down and show you how data structure and algorithm power these real-life features behind the scene. Take a look at the demo. This demo project showcases how real-time search works behind the scene. As you can type into the search bar, and match results are returned instantly. You can also switch among the different string matching algorithm and compare their performances. In this video, we will first explore a naive way to implement this functionality. Then we will introduce an algorithm that will permit us to handle this more elegantly and efficiently. If you are new to the channel, don't forget to like, subscribe, share and comment to support the channel. Code with Eno. Before we implement anything, let's understand the project structure and what is required. Our smart search bar is a Python Reflex web app that can be found in the data structure and algorithm in real life repo under the string matching pattern. And in this folder, you can see the smart search bar. And if you click on that, you will see two folders. The one below is the starter folder, where you can implement your own solution, and we have the DSA where you can find my implementation using the naive and a suitable algorithm. Let's run the starter project and see what we need to implement. Here, if you are getting this from the repo, we need to make sure that we use UV sync in order to install all the packages. Once we have that, we can use UV run reflex run reflex run. So once we have that, we can copy this and open from a browser. Alright, so this is a simple UI made up of a search bar, and here we have some selections here. Okay, radio buttons where we can select the different algorithm we want our search bar to run on, and here we have the number of operations that is performed by the different algorithm. So what we need to implement is when we search into the search bar, for example ABC, we need to make sure that the match results are displayed here, okay, in real time, and we can switch between or among these different algorithms, and we get the number of operations that is performed by the different algorithm. Coming back to the code, we'll deal mostly with the app folder. In this folder, we have the data.py. It contains a function that helps us to generate the text that we are going to use in our search. Okay, and we have the apps.py, that is the entry point to our Reflex application. It imports the different algorithm from the DSA folder. So we can see if we go to the DSA folder, we have the different module that holds the implementation of the different algorithm. We have the knife that holds for the knife implementation. We have the KMP, and we have the Boya more. You can add more algorithm here. Okay. And coming back to the app.py, we import the different algorithm here, and here we just define them. Okay, so once you add an algorithm, you have to add it here. Okay, and this here we want to make sure that we limit the search to 10 for performance reasons. Okay, and here we generate, okay, we generate the 10,000. We generate 10,000 random words that will be used for our search here, and this is just reflects helping us to set some properties, setting the query, setting the algorithm, and so on and so forth. It's not really important. What is important is this function, the run search. This is where we select the different algorithm based on the selection on the UI, okay, based on those different radio buttons that you saw. So if we have selected the knife, then the knife algorithm will run here. It returns a tuple. If we selected the KMP runs, and if we selected the BM works. The Boya more, then Boya more algorithm is going to run. And down here we have this highlight. This is just to highlight the different string match from the text. Okay, it's not really important. We don't have anything to do with this, and basically that's all we have to do. Okay, we just have to make sure that we implement the knife, implement the KMP, and implement the more. If we want to add more algorithm, we just add them, import them here. Once we import them, then we add them using an if statement down here. In the knife implementation, we'll use a put false algorithm to match all possible combination of the input pattern into the text string in order to find the position of the occurrence of the pattern. So let's say our string text is represented by S. Here we have A, B, A. And our pattern is represented by P. Here we have A, B. So what we want to do is that we want to compare each character of our pattern to the text. And if we find a match, then we'll return the index position of our string where the first character of the pattern was located. So for example, let's say we have the string here, A, B, and A. So for index equals to 0, so we start matching at index equals to 0. Okay, so we have A, it matches. A, it matches. And we have here B, it doesn't match. So we see that we don't have a match here. So we move to index 1, where we start here at index 1. So we have A, we have a match. A, we have a match. B, we have a match. So since we have a match, we return the index position of the string where the first character of our pattern was found, which is 1. So the result will be equals to, we have 1 as the first match index position that we found. Now we continue. I equals to, we move one step again. I equals 2. So we are here. So we have A, we have a match. A, we don't have any match. B, we don't have any match. All right. So the end result is that we have just one match at position 1. Okay, looking at this, we can think of the big O, or the time complexity, to be m times n minus m plus 1. Okay, so that's the worst case. Okay, the worst case. So how do we get this worst case? Now, let's say the length of our string is n and the length of our pattern is m. Okay, so if we take a look at what we just did here, we have 3 alignment, meaning that we move our pointer 3 times. So the alignment here is represented by the big O, n minus m plus 1. So that's the number of alignment we have for each of these comparison. Okay, so how do we get the alignment? How do we know this alignment is true? So let's take a look at this example here. So we have the length n equals to 5 and m equals to 3. So if we insert these values in this equation, we have 5 minus 3 plus 1, which is equals to 3. So if we take a look at the different alignment that we have here, we have 1, 2, 3 alignment. Good. So for each alignment, we compare m. We have m comparison. Okay, so we can see here, this is the first alignment, we have 3 comparison. Here we have the second alignment, we have 3 comparison, and so on and so forth. So that's why we multiply by m, which is the length of the pattern. So at the end of the day, this is our worst case scenario for our algorithm. Now let's check how this is implemented in Python. For the implementation of our knife method, we can find that in the DSA folder, where we have all our algorithm. And if we take a look at the knife.py, we will have this implementation. Okay, so we can see our knife method takes in, or our knife function takes in 2 parameters, the text and pattern or string. And here we find the length. This represents n, like we saw in the demonstration, which is the length of our string, of our text string, and this is the length of our pattern. And here we just maintain an index, okay, starting from 0. Here this is a list that is going to contain all the matching indices, and here this is a comparison that just add up to represent the number of comparison that we have for this particular algorithm. So here we loop through the alignments, the number of alignments. We had we had the equation already from the big O, the worst case that we saw in the demonstration. So we make sure we loop through the number of alignments that we need for this particular algorithm. And here we just make sure that for each pattern in that alignment, we compare the character in the text against the character in the pattern. So this just makes sure we are calculating the number of the operation that we need. So once we have, if we have a match here, we increment the count. Okay, and at the end of the day, we check if the count is the same as the length of the pattern. If it is the same, it means that we have a match. Then we go ahead and add the index in the match list. If we don't have any match, then we go ahead and increment the we increment I, that is, we move to the next alignment. Okay, and we do the same thing over and over till we are done with the alignment. So once we are done, we go ahead and return a tuple, which is made up of the list of indices that we found and the comparison. So now if we go to our web app, then we can see we have selected knife, and if we go ahead and search, let's say NMG, so we can see here we have NMG, we have 3 results, okay, that's been displayed here, and we have the number of operations for our naive implementation, that is 180,000 operations. All right, so let's move on to the next algorithm and see how this will be made better. All right, so we just took a look at the knife implementation, and we can say it did the job. Okay, we were able to search and we saw the match string being displayed on our web app. But when we take a look at the number of operations, we can see that there's a lot of operation going on. We had 180,000 operations. This is because the knife implementation performed a lot of unnecessary comparison. Now let's take a look at an efficient algorithm that can help us reduce this number of operations. When we talk about algorithm, an efficient algorithm in the space of string matching pattern, we can think of the KMP, or the Knuth-Morris-Pratt algorithm. Let's see how it looks like. The KMP pattern matching is based on the idea that the overlapping text in the pattern itself can be used to immediately know at the time of a mismatch how much the pattern should be shifted in order to skip unnecessary comparison. The KMP uses pre-computed values of a prefix function to determine how much pattern, or how much the pattern should be shifted. Basically, it starts with the first character of the pattern, then incrementally adds the next character while checking if the first and the last character or group of characters of the substring are the same. Alright, so let's say we have this text string, Ababa, and we are going to fill up this table. So this table contains the indices, or the index, the pattern. We will have a comparison here to check if the prefix equals to the suffix, and we have the value. So at index 0, what is the value at index 0? We have A. So here we can say the prefix is the same as the suffix because we have just one value. So basically this is 0 for all cases. Okay, the index at 0 is always 0. So when we go to index 1, we add the value at index 1. So we have A and B. So we see we add, okay, so we maintain the value at index 0 and we add the value at index 1. So we have AB. So when we check the prefix and the suffix, we see that there's no match. So it remains 0. So we move to 2, we add index 2. So it becomes ABA. So we can check the prefix is the same as the suffix. So we have just one match here, which is A, and we have 1. So when we move to index 3, we add A, B, A, B. So we can see if we check single characters, we can see that there's no match. But when we move to 2 characters, we can see AB is the same as AB. So the prefix at AB is the same as the suffix AB. So here we have 2 match, AB. So we put 2. So we move to index 4. We have A, ba, ba. So we can see if we check the first character A, and the last character we have a match. But that's not all. Okay, we can check, we can see ABA or AB is not the same as BA. Okay, but if we move the third to the third character, we can see ABA is the same as ABA. So ABA here is the same as ABA here. So we can see at the end of the day we have 3 matches. So here we have 3. So this is how the prefix function is being evaluated. So now let's see how this is implemented in Python. Alright, so for the implementation of the prefix function, we can find that in the KMP module of the DSA folder. So once we have that, we can see this is the implementation. And to demonstrate the implementation, we're going to use this string. And we can see if we use this string, it has A, B, A. All right. And what we do is that when we pass this pattern, okay, let me call it pattern, not string. Okay, let me call it pattern, not string. So once this pattern is passed in this function, we find the length of that pattern and we create a prefix list, okay, with zeros according to the number of patterns that we have. So let's say this is the prefix list here. And remember from the previous section I said the at index 0 the value is always 0. So that's why we have here the prefix list start with 0. Okay, and our for loop start at 1 because we have already taken care of index at 0 here. Okay, so let's say our k for the first loop here, our k equals to 0 and our cure equals to 1. Okay, so when we check line 6, we see that the while loop, the first condition of the while loop doesn't the first condition of the while loop is false. So we skip line 7 and move to line 8 where we check p of k, which is 0, if it is equals to p of cure, which is 1. So if we check here, at 0 we have A and at 1 we have B. So we see that they're not the same. So k is still maintained 0. So here we put 0 here. And we move to the second loop where k equals to 0 and cure equals to 2. So we see that condition 6 is also false. So we move directly to condition 8 where we check if p of 0 equals to p of 2. So p of 0 is A and p of 2 is A. So we can see that this condition is true. So if the condition is true, what happens? We increment k. So k becomes 1. So we put 1 here. Okay. So for this next loop, we see that k equals to 1 in the next loop, while cure equals to 3. So because k equals to 1, we can see the condition at line 6 is true for the first part. That is k is greater, while k is greater than 0. So we check the second condition, that is p at 1 is not equals to p at 3. So let's see, p at 1 is b is not equals to p at 3 is 0, 1, 2, 3 is A. So see that the condition is true as well. So because the condition is true, we get the new value of p. The new value of p is coming from the prefix list at this index. So we say new value of k becomes PL. K minus 1 is 0. So yeah, the value at index 0 from the prefix list is 0. So the new value of k becomes 0. So we can see now that the condition here at 6 fails because here it's a while statement that check if k is always greater than 0. So because it fails, it goes back to line 8 where it checks p of 0 equals to p of 3. So we can see now p of 0 is A, while p of 3 is A. So k is increment back to 1. So we have 1 here. So same thing happened here. So k equals to 1 for the next loop. while cure equals to 4. That is the last loop, right? And because the condition k greater than 0 is true, we check the pattern, we check the next condition, which is pattern we check this condition here. Pattern at k is not equal to pattern at cure. So we say p at k is 1, is not equal to pattern at cure is 4. So pattern at 1 is b, is not equal to pattern at 4 is a. So because this condition is also true, we get the new value of k, which is pl of 0, which is equals to 0. So now, because the while loop at line 6 is false, we skip and go to line 8, which check p of 0 is equals to p of 4. So p of 0 is a, p of 4 is a. So we can see we increment again k equals to 1, and we have 1 here. So at the end of the day, this is the value of our prefix function that we are going to return and fit it in the KMP in order to help us skip the number of patterns when we meet a mismatch. Alright, so for our KMP algorithm, we have this, found in the KMP module. This is where we have our prefix function. So we can see our prefix function is just above. So when we go down, we can see our KMP function. So it takes in the text and the pattern, and what it does is that it gets the length of the text and length of the pattern. It gets the prefix list from the pattern, and it defines some parameters here for example, to maintain the matches and also the comparison. So let's take a look at this this demonstration here. So let's say, for example, we are dealing with the string AB, AA, BA, and the pattern AA. So we want to see if we have a match in this string. So the prefix list that we can get from the pattern will be 0, 1. So looking at this pattern, we can also already tell that at 0, it will be 0. At 1, we can see at 1 we have the prefix is the same as a suffix, so that's why we have 1 here. So here is the match. So this is empty, by default. So when we come here at line 27, the first loop is at I equals to 0. At I equals to 0, we also have cure equals to 0. So cure equals to 0. So what we do is that we come at line 29, we check this condition. We can see here the first condition of our while loop is false, so we skip line 30 and goes to line 31, where we check if the pattern at cure, which is 0, is the same as the string at 0. So if we replace this by their various characters, we can see we have here A, and here we have A as well. So it's the same. So we go ahead and increment cure. So we can see here, if they are the same, we go ahead and increment cure. And we check if we have already done a complete match. Here we check if the number of comparison we have had, the number of matches we have had is the same as the length of our pattern. So here we check if cure equals to m. So cure at this stage is 1, but m is 2. So we can see here, this is the length of the pattern, which is 2. So it's not the same. So we go ahead and we skip to the next loop, which is I equals to 1, while cure is maintained as 1. So cure was maintained as 1 here. So we can see here now that on line 29, the while loop, the first condition of while loop is true. So cure is greater than 0. So we check the second condition, which is this one. So we check it at P at cure, which is 1. if it's not the same as text at I, which is 1. So if we replace with the various characters, we can see here is A, and it's not equal to here is A as well. So this condition is false. So we skip to line 31, where we check if P of 1 equals to S of 1. So have here A equals to A. So we see that A is equal to A. So what do? We increment cure. So cure becomes 2. So now we check again the if statement at line 33. Cure equals to M, which is true because 2 equals to 2. So if 2 equals to 2, what do? We evaluate the index, okay, where we first got the match, and we assign it to the matches. So the evaluation says it should be I minus M plus 1. So we have here I equals to 1 minus 2 plus 1, which is equal to 0. So our first match, the first character begin at index 0. That is where we have our match. So go ahead and add it here. So we have 0 here. Okay. So we move on. So once we have that, we can see here we get the new value of cure. So our new value of cure would be equals to the prefix list of index cure minus 1. So cure originally is 2. So cure minus 1 is 1. So we get the value at index 1 from the prefix list, which is equals to 1 here. Okay, so our new value of cure is 1. So we move at I equals to 2, where we have cure equals to 1 from this evaluation here. So once we have that, we see that the while loop at 29, the first condition is true, so cure is greater than 0. So we check the next condition. P at 1 is not equals to S at 2. So let's replace with the values. P at 1 is A, while S at 2 is B. So the condition is true. So what do? We get the new value of cure. New value of cure will be the prefix list at cure minus 1, which is 0. So here we can see here the value here is 0, so we return 0. So our new value of cure is 0. That means the while loop here will fail, and we move to line 31, where we check P at 0 equals to S or string at 2. So we have here A equals to B, right? So A here, and 0, 1, 2, B. So this is false. So since it is false, what do? We go to the next loop, which is I equals to 3. Here we have what? We have cure equals to 0, because it was set here. Okay, it was reset here to 0. So at I equals to 3, we have the condition at 29, which is false. So we move to line 31, and we check P of 3 equals to S of, P of 0 equals to S of 3. So we say P of 0 is A, and S of 3 is A as well. Okay, so that means cure will be incremented to 1. So we check if the condition cure equals to M is true. We say 1 is not equals to 2. So we go ahead and skip that loop. Okay, so we are at the end of the loop at this point. Okay, I think so. This is 0, 1, 2, 3. So we are at the end of the loop. So we only saw one match, which is at index 0. So basically, this is what our code here is doing. And I almost forgot to indicate the worst case for the KMP. And we already saw that for the naive we had big O of m times n minus m plus 1. But for the KMP, we have O of m plus n. So we see that this is a significant increase in performance, right? So how do we get this O of m plus n? The KMP has the prefix function that we saw, prefix function, and the prefix function actually has O of m because it kind of like loop through the pattern and extracts, or loop through the pattern and get some values. Okay, so it has O of m, and the KMP itself has O of n plus, okay, plus this O of m that we receive from the prefix function. So altogether, the KMP has a time complexity of O of n plus m. Okay, moving back to our live demo, we can select KMP here and we do a search. So let's say we do this search AB, we can see a maximum of 10 results coming up with AB highlighted. And if we check the number of operations here, we have 4,176 operations. But if we select naive, we see that it's increased to 7,000. Okay, so compared to the KMP has lesser operation. Here we have 80,000 operations, whereas in the naive we have 180,000. Alright, so we have seen two implementations, the naive implementation and the KMP implementation. But we've seen that there's a significant increase in performance when we use the KMP because of the strategy that the KMP put in place by using the LPS array, or the longest prefix which is also suffix. And this helps us to skip unnecessary operation by reusing previous matching information. Thank you for watching. Be sure to come back as we keep exploring data structure and algorithm and how they are used in real-life scenarios. As always, you are encouraged to review the standard code and build your own implementation if you believe there's data structure or algorithm that works better than the KMP we just explored. I would love to see your version. You also have the possibility to implement the Boyer-Moore algorithm and see how it performs. Go ahead and fork the repo, implement a solution, and submit a pull request. And if you're new to the channel, please don't forget to subscribe, like, share, and comment to support the channel. Code with Eno. See you in the next video.